All right, so this video here, we're going to cover the fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus, so we'll go through each one with some examples for each one. And it truly is fundamental. This is really foundational to everything we've been working on with integrals and derivatives. And so what we're going to focus on today is the ability, first of all, to evaluate a derivative without an antiderivative without a calculator, or a definite integral, I should say. And then we're also going to talk about the connection between derivatives and integrals. So let's start with part one, where we are defining the function capital F of t as the antiderivative of lowercase f of t. So essentially what this formula here is telling us, this first part of the fundamental theorem of calculus, is that in order to calculate a definite integral meaning that we have a lower bound and an upper bound, you antiderive the function on the inside. So we've been working on antiderivatives all the way up to this point. And then you evaluate the antiderivative at the upper bound and subtract that, or subtract from that the antiderivative evaluated at the lower bound. And when you do this, you are calculating what is called signed area. So if I have a function here that looks something like this, and these are my bounds for my integral, then any of the area between the function and the x-axis that exists below the x-axis is considered negative area. And then any of the area that exists above the x-axis, this is all considered positive area. And so when you calculate the antiderivative using the fundamental theorem of calculus, you are finding the combined signed area. Signed area meaning that this actually counts for negative area and this actually counts for positive area. And so you would get the total of that. So that is what we're calculating when we find the antiderivative. Let's take a look at some example problems here. So here we've got just a basic antiderivative. It's a polynomial, so we don't have to do any kind of fancy things with it. We're going to apply the power rule here. So I'm going to start with 6x squared. I'm going to add 1 to that exponent and divide. So I have 6x to the third divided by 3. My next term here, the x of course has an exponent of 1. So I'm going to add 1 to that and divide by our new exponent. So I have 2x squared divided by 2. And then my last term here with a constant, I'm going to add an x to it. Now, one of the things to note with the definite integral is that we do not need a plus c. And that's because if I'm going to be subtracting my function evaluated at them, then the c is going to cancel itself out anyways. So it doesn't really matter what the constant is when I'm calculating a definite integral. So we no longer will use the plus c on the definite integral, but remember, you cannot forget those on the indefinite integral. Okay, so when you're just finding an antiderivative, you have to remember that plus c. So I'm going to simplify here. 6 divided by 3 gives me 2x to the third. And 2 divided by 2, of course, gives me x squared minus 3x. This is often notated with a straight line here, where you write the lower bound at the bottom and the upper bound at the top. And this is just saying that I'm going to evaluate this function here, my antiderivative, at 7 and at 1. So starting with 7, I'm going to plug 7 into in for x, minus 3 times 7. And then I'm going to evaluate my function at 1. So I'm going to plug in 1 for x. So I have 2 times 1 cubed plus 1 squared minus 3 times 1. And now here I'm going to go ahead and work this out. 7 cubed is 343. 2 times 343 plus 49 minus 21. This is going to be 686 plus 49 minus 21. And what do we have here? 5, carry the 1, 5. 755 minus 21, which is going to give me 734. And then over here, all these ones are much easier to calculate. So I have 2 plus 1 minus 3, which is going to come out to 0. And so 734 would be the value of this integral. And remember that in finding a definite integral, what we're saying is that the area under this curve, or I should say between the x-axis and the curve, from 1 to 7 is a total of 743 units. I would encourage you to punch this into a calculator and take a look at that quadratic there and see what that looks like. So here's another example. This one's in here just to kind of have some discussions about those mathematical things that we do to numbers. So this one with the square root of 2 over x, we should start by rewriting this so that it looks like something that we can actually anti-derive. So I'm going to rewrite this as the square root of 2 over the square root of x. That's my first step here. And then I want to rewrite the square root of x as a power, and I'm going to move it up to the top to make it a negative. So what I have is the square root of 2 times x to the negative 1/2. So square root of 2 is just a constant, so we can go ahead and move that to the outside of the integral. And then we have x to the negative 1/2 that needs to be anti-derived. So I'm going to add 1 to the exponent, which means I'm adding 2 over 2, and divide by that new number. So now I have the square root of 2 times x to the 1/2 divided by 1/2. Remember, we're not using a plus c because we're just evaluating our function at each of these points. And so I have the square root of 2, or 2 times the square root of 2, x to the 1/2, which I can also go ahead and put this x inside there with the 2. So 2 times the square root of 2x. And let's evaluate that at 1 and at 8. So I'm going to start by plugging in 8. When I plug in 8 here, I get 8 times 2, which is 16. And I guess I should show this. The square root of 16 is 4. So I have 2 times 4, so this simplifies to 8. I'm subtracting that from this function here, evaluated at 1. So 2 times 1, which is just going to be 2 square root of 2. Now, as we're doing all of these kinds of problems by hand, you'll notice that now we get what we would call exact answers. We're not plugging it into a calculator. We're not rounding to 3 decimal places. So this is an important skill as well to be able to do these problems by hand where you're not relying on a calculator. With that being said, let's do some trig work by hand and see what those problems come out to. So this one here, again, we're just looking at pretty basic antiderivative. We've got addition here. We don't have to do any kind of rewriting. So I'm going to antiderive this function, and I get 2x plus sine of x for my antiderivative. Okay, we add that x there, and then the antiderivative of cosine of x, you would want to use your cheat sheet if you're still working on those, is sine of x. I'm going to evaluate this function from 0 to pi. And so I start by plugging in pi for x, so I get 2 pi plus sine of pi. And then I evaluate it at 0, so minus 2 times 0 plus sine of 0. Okay, so here I've got 2 pi, and a sine of pi, if you look at the unit circle, is equal to 0, so that just comes out to 2 pi. And then over here, sine of 0 is also equal to 0. So I'm just subtracting 0 there, so I get 2 pi. So this is telling me that the area under this function, from the function to the x-axis, from 0 to pi is equal to a total of 2 pi. Okay, let's take a look at an example here where you have to use a skill you just learned, and that is use substitution. So the fact that I have a product here is an indication that I can't just solve this the way that it looks. I could multiply it out and do it that way if I wanted to, but let's go ahead and practice our use substitution and also have a discussion about what that does to our bounds. Okay, so use substitution has a little bit of an extra step when we've got bounds on our integral. So the first thing I need to do is identify what my u is, what that inside function is. For this problem here, that's going to be x to the third plus 8. And then I derive u. So I get du dx is equal to 3x squared. And then of course I want the dx on the other side, so du is equal to 3x squared dx. And here I should start to see that I've got a little bit of that. We're going to have to move the 3 over so that we can substitute properly. And so 1/3 du is going to be equal to x squared dx. So let's begin doing some substitution here. That x to the third plus 8 gets substituted with u, so I have u squared. And then the x squared dx is going to be substituted with 1/3 du. Now the important thing to note here is that I've just changed my variable from x to u. And so my bounds also need to change. These bounds right now are defined in terms of x, and they need to be changed to terms of u since I'm working with an integral in terms of u. And so the way that that is done is by plugging this in for x to find out what u would be equal to. So I'm going to plug in -2 for x, and -2 to the third is -8. So -8 plus 8 is 0. So the lower bound on my integral in terms of u is 0. And then for the upper bound, I plug in 4, and 4 to the third is 64, and 64 plus 8 is going to give me 72. So my upper bound in terms of u is 72. Now the nice thing about this is that once I've done change these bounds, I do not have to go back into terms of x to evaluate this integral. So here I'm going to move the 1/3 out in front because that's a constant. And then I'm going to add 1 to the, I guess I shouldn't shorthand that. I'm going to add 1 to the exponent now and divide by that new number. So I have 1/3 times u to the third over 3. And this is going to be evaluated from 0 to 72. So again, I'm not going back in terms of x because I just put my bounds in terms of u. If you like going back in terms of x, that is fine. It is very, very important that you can recognize that this integral is equivalent to this integral. That's a really popular AP question, to have you draw that connection to make sure that your bounds are changing, that the constant is correct in the front. So that's something to just be aware of as far as having the skills that you need to be successful on that test. Okay, so here we would plug in, these are ginormous numbers that I'm not going to do by hand. So 72 to the third power, and then I'm going to divide that by 9. And when I evaluate that, I get 41,472. And when I evaluate this at 0, it's just going to come out to 0. So again, this is measuring the area under the curve from, well, in terms of x, from -2 to 4. Okay, one last example I want to discuss is a trig example with u substitution again. So we have an inside function here of 2/3 x, and I want to derive this, so du dx is equal to 2/3, which means that du is equal to 2/3 dx. Now this one's a little bit of an easier substitution. We don't have a 2/3, so we need to divide that on both sides, and we're going to end up with 3/2 du is equal to dx. So all we're substituting in here is the dx. Okay, that 3/2 can be moved to the front. And then I have cosine of u du. Now my bounds again, I want to change. So I'm going to plug in 0 for x, and my lower bound becomes 0. And then I'm going to plug in pi over 2, and so my upper bound becomes pi over 3, because pi over 2 times 2/3 is pi over 3. Then I'm going to find my antiderivative. So the antiderivative of cosine of u is sine of u, and that is what I'm evaluating from 0 to pi over 3. We need to know our unit circle well, so get that out and study that if you're still working on those values. But I have 3 over 2 times sine of pi over 3, and sine of pi over 3 is going to be equal to the square root of 3 over 2. And then I have 3 over 2 times sine of 0, and sine of 0 is going to be equal to 0. And so what I have here is 3 square root of 3 over 4 for my final answer. So this is just another point here where we're seeing that having an exact value versus having a decimal answer. So we're not using a calculator, we're now using the fundamental theorem of calculus to evaluate these integrals. Okay, if you need a little more practice on this, you can take a look at page 293 in the textbook. Numbers 5 through 33 odd have plenty of definite integrals. And then if you flip on over to page 307, you're going to see some definite integrals where you need to use u substitution. All right, check into the next video for part 2 of the fundamental theorem of calculus.